In this video, we're going to be studying in quite a bit of detail the photoelectric effect. But let's start off with a wee bit of history. And by the end of the 19th century, it had been quite firmly established that light behaves as a wave. Christian Huygens' wave theory can be used to explain how electromagnetic waves can refract, diffract, and interfere. And if you recall from the last chapter, we talked about Thomas Young's double slit experiment, which provided experimental evidence for this wave theory that Christian Huygens had established. And then we had James Clerk Maxwell's electromagnetic theory, and we also had Heinrich Hertz's various experiments that all demonstrated the wave-like properties of the electromagnetic waves. However, in the late 1800s, 1887 to be specific, Heinrich Hertz began to experiment and demonstrated that cathode rays could penetrate very thin metal foil, such as aluminum. And at the time, J.J. Thomson noted the electric and magnetic fields can be deflected by cathode rays. And so he believed that these emitted charges were tiny negative charge particles that were basically electrons. We called them photoelectrons because they came from a photoelectric effect. The photoelectron is essentially an electron, which we call the photoelectron to indicate the origins of the electrons. Okay, let's discuss the experiment. You're expected on the AP exam to know how to describe the typical photoelectric effect experiment and explain the experimental observations. Around 1900, Hertz and one of his students named Philip Lenard built a glass tube, as shown here in the diagram. Now, often this glass tube is called a phototube, and it's evacuated, so it means that there is no air in here, so we don't have to worry about air resistance. Inside this glass tube, you may notice that there are two kind of plates or two electrodes that are facing each other. One is negatively charged, which would be this plate right over here, the metal plate, and we typically call that the emitter or the cathode. And the other plate over here that's facing this negatively charged plate is the positively charged anode, or also called the collector. Now, what was found is that if you were to direct a light beam of short enough wavelength onto this nice clean, let's call it a photosensitive metal surface, then this incoming light would cause electrons, or as they call them, photoelectrons, to be ejected. And that's what you see, these electrons being ejected or liberated from this metal surface. These ejected electrons or photoelectrons will move then from this emitter towards the collector. So it'll move from the cathode over here to the anode, and then they'll start to move through this circuit, and you'll register current in the circuit. Sometimes this measured current was called a photoelectric current. Now, you may not realize this, but the photoelectric effect is used in many devices that you use on every day, such as those automatic sliding doors that you walk through in shopping malls that use some kind of electric eye sensor to detect motion, or a light meter that is used on a camera or a video camera. Over here to the right, you'll see other diagrams of the same experiment of the photoelectric effect. So here's your photocell or your phototube, and then you have the metal plate that's ejecting the electrons, and then the collecting wire that is picking up these electrons and then causing current to show up on the ammeter. And this is another one, sort of like a top view of that same experiment, collecting wire, and you can see these electrons being collected over here at the collecting wire. And essentially it's the same thing. You have an incoming beam of light that is causing electrons to be ejected out of this metal surface and then move through this circuit. So to dive into the experiment and really understand the observations that you're expected to know, I'm going to use a computer animation from PhET. So if you Google PhET, P-H-E-T, and then like photoelectric effect under, you should be able to find that actual animation, and you can go ahead and play along and try it on your own. I think it's best that you try it yourself as well after you watch this video and prove it to yourself what's happening. So here we are with the photoelectric animation. We have a lamp here. I'm going to turn that on. Give it a little bit of brightness here, and you can see these tiny blue particles that are being ejected. These are called photoelectrons. And over here is the metal, which is calcium, and we call this the emitter or the cathode. And over here, this is the anode or the collector. And since there are electrons that are flowing through this circuit, we have current being registered. So now let's make some experimental observations. What we want to look at is how does the intensity of this lamp affect the current that is being measured in our ammeter. So I'm going to plot a graph of current and intensity, and watch as I increase the intensity. So as I make this lamp brighter and brighter, you'll see a larger and larger current being shown up in the circuit. And so hopefully you can see that there is a direct relationship between current and intensity. And as long as you're not at like zero intensity, which you get no photoelectrons, as long as you have a little bit of intensity, like 2%, you're still going to get photoelectrons that are being ejected, and you'll still be getting current being registered. Okay, next up, second important observation we should make is what we want to do is if I turn on this lamp again, you can see that there are photoelectrons that are being ejected. And you may notice that they all have a certain amount of energy, or kinetic energy to be specific. What we want to do is we want to determine the amount of energy of these electrons. And the way we're going to determine the energy of these electrons is we're going to be using this voltage source over here to essentially stop the electrons from flowing through the circuit. You can see that there's a current being registered here. So what we're going to do is we're going to make this collector plate here, we're going to make it negatively charged by reversing the potential of this battery. So I'm going to suddenly switch it over here, and you can see I have now a negative potential. And as I increase this negative potential, you'll see the current is lowering and lowering and lowering until eventually I get to a current that is zero. And when I get to that zero current here, I've reached what we call the stopping potential. All right. Now, just to show you what the graph looks like, let's plop that up as well. So here's the current and versus the voltage that I have across the battery. As I increase the voltage back to zero, you can see that there is this direct relationship between current and voltage. But as I increase the voltage now and make this actually positively charged, suddenly these electrons will be moving even faster, but the current doesn't change at all. And the reason for that is because this lamp is coming in and only knocking out so many electrons per second, right? Which depends on the intensity of the lamp. So what would happen if I were to change this lamp to a weaker intensity? Let's take a snapshot of this graph here. This is the graph that you can see here. And I'm just going to take a picture of that graph and just place it over here. All right, what we want to do now is we're going to change the intensity of our lamp. Let's go back to, say, 0 here. And we're going to go to a less bright lamp over here. So there's a weaker intensity. And now we're going to reverse the potential. Let's see, if you go increase it, you get this nice horizontal line over here. And you'll notice that the current is less than what it was before. And as I decrease the potential and get this negative stopping potential until the current becomes 0 right there. Oh, it's exactly the same as the other one. I'll take a picture of that and see if you can notice that. If you look at the two graphs, you'll see that their currents are less. Yes, they're less because, of course, you have less intensity, you'll have less photoelectrons being ejected and less current that will flow through the circuit. However, you may notice that this x-intercept right here at negative 2.8 volts, which represents the stopping potential, is the same for both graphs. So just to repeat once again, as I turn this lamp up here, you see there's photoelectrons being ejected with a certain amount of kinetic energy, and as I reverse this potential until the current becomes 0, and right at that point right there, that point where it just starts to become zero current, this is known as the stopping potential. All right. What we're essentially doing is we're causing the electron to lose all of its kinetic energy before it reaches this plate, and so it won't actually travel through this circuit anymore, and hence there'll be no current. Now, this potential here, this negative 2.8 volts, can be used to determine the maximum kinetic energy of these fastest photoelectrons as they leave the metal cathode. The kinetic energy, we'll just write here as K max, is equal to the potential energy that it loses, the electric potential energy, which is equal to Q times delta V. Whoops, that should be a delta V here, which I'll write, instead of Q, we're going to write as E for the charge of an electron times V sub S for the stopping potential. So essentially you could rewrite this kinetic energy as 1/2 mV max squared equals EVS. VS represents the stopping potential, which was negative 2.8 volts. And that, if you know that potential and the charge of an electron, and say the mass of the electron, you can find out the maximum velocity of these electrons as they're being ejected. So that's one key equation that we'll be using as we go through the photoelectric effect. So we now know that a brighter and brighter light will knock out more and more photoelectrons, showing that the current is directly proportional to the intensity of the light. And we also know that we can stop these electrons by reversing the potential of the battery until you register a zero current. And when you reach that zero current, that's when we have that stopping potential. Now that stopping potential that's listed here can be used to determine the maximum kinetic energy of the electrons. Next, what we need to look at is how the frequency of this lamp is related to the energy of these photoelectrons that are being ejected from this target metal surface. Now let's watch what happens as I vary the color of the light that shines on the metal. As I increase the frequency, you'll see that the energy of the photoelectrons increases linearly. And similarly, as I decrease the frequencies to lower and lower frequencies, the electron energy decreases until you reach this special point right about here, and suddenly you'll notice that there are no photoelectrons being ejected. Now, at this specific frequency right here, we call that the threshold frequency, or this wavelength here is called the cutoff wavelength. Depends on whether you're looking at the frequency or the wavelength. If you are above this threshold frequency, you get photoelectrons that are being ejected. If you're below that threshold frequency, then you do not get any photoelectrons being ejected. Now, I'll just take a snapshot of that particular graph. This is for sodium. Now, if I change to a different metal, let's just kind of put this over here, I guess. And let's take a look at changing this metal, say, to copper. And then now I'll once again vary the frequency here, and you'll get once again this curve right here. And I'll take a snapshot of that. And you may notice, let's take a look at the similarities of these two graphs. So here, I'll bring this one up a little bit higher here. You'll see that they both have the same slope. Now, the slope of these two graphs represent Planck's constant. However, their x-intercept here and here is different. That's because each metal has its own threshold frequency. And then down below here, we'll have a y-intercept, and I'll talk about that soon. So now let's return back to the notes and analyze these graphs in much more detail. And this is where Albert Einstein comes in here. So back to our notes, there's the picture of the setup, and we talked about several things that are listed down here. So we were discussing earlier the stopping potential, and the stopping potential is denoted with a V sub S, and by knowing the stopping potential and the charged electron, we could find the maximum kinetic energy. or even the velocity, the maximum velocity of these photoelectrons. The threshold frequency we talked about as well, and this depends on the type of materials. Most metals will fall in the UV range, somewhere between 200 to 300 nanometers as a threshold wavelength, or sorry, a cutoff wavelength. Okay, now going on to the next page of the notes, you'll see we have Einstein's explanation. Now this, in 1905, the same year he published the special theory of relativity, he won the Nobel Prize for his explanation of the photoelectric effect. Actually, most people thought he was going to get this, his Nobel Prize for the theory of relativity, but interesting, he actually got it for this. Einstein basically postulated that light coming from the lamp consisted of small bundles of energy, which he called photons. And when a photon strikes the surface of the metal basically absorbs that energy. And it will knock out a single electron for a single photon. Now, the energy transfer that comes into here is kind of like a all or nothing process. Either the electron gets either all of the photon's energy or none of it at all. Now, it depends on the energy that is needed to knock out this electron. The analogy you might want to use is up to you. I mean, there's a different analogy. This is one I just thought of. You could kind of think of it as like your electron is like trapped in this metal surface, like he's in jail. So it's like your uncle who's stuck in jail, and you're trying to liberate him. So you can call the amount of energy to liberate him, we're going to call that the work function. And then any extra money or energy he gets, he'll basically spend it, like kinetic energy. So there's a certain amount of energy to knock him out, that's the work function, and then any extra energy that comes out that he has in excess of that will basically come in the form of kinetic energy. Now, if you look at the graph down below here, you can see that we have kinetic energy, or the energy of the electrons, plotted versus the frequency. And here, right here, is the cutoff wavelength, and the slope of this graph represents Planck's constant. So if you think of this equation, remember it's like a y equals mx plus b. We have plotted on the y-axis, we have kinetic energy, maximum kinetic energy. The slope of this graph represents Planck's constant, which is h. The x-axis is the frequency, f. And then the y-intercept, which is down here below here, we have a negative y-intercept, so we're going to put a minus sign, and then this little symbol here, and this symbol here represents what's called the work function. It's like the bail amount that you need to give your uncle so that you can yank him out of jail. All right, it's the, in physics terms, it's the minimum amount of energy that is needed to pull the electron out of the metal. The work function, by the way, depends on the type of material you're using. If you look ahead in your notes, you'll see a whole list of different metals and their different work functions to liberate those electrons. Okay, so the equation that shows the maximum kinetic energy equals the HF, which is really, if you think of that, this is the photon energy, and then we have the work function. Really, this equation is just an equation of conservation of energy. If you think of it, when you have this photon that's coming in here, you have energy of the photon, which is h times f, and then there's a certain amount of energy to knock it out, that's called the work function. And then any excess amount of energy is then turned into is kinetic energy of these photoelectrons. So imagine the energy, total energy of the light gets absorbed by this metal, or by that one single electron. Part of that energy is going to be used to liberate the electron, and the rest of it goes into kinetic energy. So when you look at this equation down below over here, this is an AP formula right in here. This is really just a statement of the conservation of energy. And this HF represents the photon energy, and this little funny symbol phi here represents the work function. This is the amount of energy to liberate the electron. And the difference between these two represents the kinetic energy. Now, it all depends on whether that photon energy is larger than the work function. Now, if the photon energy, for example, if you're using sodium metal and you send in a photon energy that is less than, say, 2.46 electron volts, then now you're not going to get any electrons liberated. It's because you can't liberate. You kind of think if your uncle can't get out of jail, if it's like the bail amount is, say, $200 and you show up with 150, you're not going to liberate them. You got to have an energy that is greater than the work function. Now, also we learned earlier, and this is also shown in the notes right here, that the kinetic energy can be determined of these photoelectrons if we know the stopping potential. So another graph that you could plot is, let's use the fact that 1/2 mv max squared, which is equal to k max, is also equal to the charge of an electron times the stopping potential. So you could replace this kinetic energy with E times Vs, which is the stopping potential, which is equal to HF, the photon energy, minus the work function. Then, if you divide everything by E, here, you'll get the E that cancels out, and so you might get this equation as well shown. And so another graph that I did not show you, I didn't plot, but was we could have plotted the voltage, the stopping potential, versus the frequency. And you would get a similar graph with a cutoff frequency, except the y-intercept won't be the work function, but it'll be the work function divided by the charge of electron. And the slope of this graph won't be Planck's constant, but it'll be Planck's constant divided by the charge of an electron. Now, you're expected to know how to do calculations that involve this equation here and this equation over here. And you'll see that in the upcoming examples. And you're also expected to be able to sketch and interpret the graphs, particularly the stopping potential versus frequency, and then also the maximum kinetic energy, or the energy of the electrons, versus the frequency. And understand that this, in this particular graph, the slope represents Planck constant, and then the y-intercept represents the work function. But if you plot the stopping potential versus frequency, the slope represents Planck's constant divided by E, and the y-intercept represents the work function divided by E. Okay, this is quite a bit of information and quite a long video. The best way to, I guess, to start to understand it is to play with that animation, and then also to start doing the next examples. And one final note that I should mention too is that up here in the notes I have listed puzzling experimental results. And I've summarized why this particular experiment, the photoelectric effect, is so pivotal in the history of physics. You imagine Heinrich Hertz, who's like known as like the sort of the father of wave theory, and his last experiment that he does basically goes against that whole theory, and he basically ends the era of classical physics and thus begins the modern physics era. And this whole experiment can't be explained by classical physics, wave theory, Christian Huygens theory. Can't be explained by that. And it was Einstein's explanation of this that led to the new ideas in this new era of quantum physics. So you should take a few minutes to kind of read through these puzzling experimental results and understand why the photoelectric effect was inconsistent with the classical wave physics model, and actually provided evidence for the photon nature of light. And that's sort of summarized through here when we talked about how the intensity of the light is directly proportional to the current. That can't be explained by classical physics, and so forth. So read through here and make sure that you understand that as well. That sometimes comes up as multiple choice questions, conceptual ones. Okay, long video, but hopefully you understand what's going on with the photoelectric effect.